Hi everyone, welcome to this video and welcome to my channel. So this video as well, I'm going to follow the trend just like my last few videos, and I'm going to start this video with another question, rather a couple of questions, right? So let's say you have a Linux host or a Linux server. From within that Linux host, you want to make an upstream call to a service which is also hosted in your same network or maybe in a different network connected to your network using a router or something like that, or router or switch. But the bottom line is there is another service whose IP you know, right? You know that service as IP, and you want to make a call to that upstream service from your Linux host, right? How would you do that? It's pretty simple, right? If you know the IP and if the IP is accessible, you can always connect to that service, right? No problem at all. Now let's say there is a this service. This is highly available. By highly available, I mean it has got multiple instances running in different servers, all in your same network. Again, all these different hosts in your network are also accessible by their IPs. So let's say the service that you want to make a call to, it has got multiple instances. Just like it happens in typical highly available services, this service is deployed into multiple instances or hosts present in your network, and now you want to make a call from your Linux host, from your main Linux host to this service, such that your calls are distributed among all the different hosts on which the service is deployed, right? So you don't want the call to always land on a single host, but you want to distribute it among all the hosts on which the service is deployed. So how would you do that? How would you contact or make a call to such an upstream service which is deployed on multiple hosts and get back a response, right? One of the easiest solutions that comes to our mind is, deploy just another Linux host and set up a proxy. In other words, set up a load balancer on that particular host. Then your Linux host basically connects to the load balancer, and the load balancer takes care of distributing the traffic among all the different servers on which the service is deployed. And that's how you can make the call, and the load balancer can provide you with one or more virtual IPs, or that box can have one or more IPs, and each IP can correspond to a particular service, or maybe you can do some sort of vhosting by which, using the host header, it knows which upstream, which service cluster to call, right? So that sounds all very sophisticated, right? You need a load balancer, you need a separate Linux host, or maybe you can also set up the web proxy or the web server or the load balancer on the same host as your Linux host from which you want to make the call. You can do that as well, right? But for this, the very first thing that you need is a load balancer, right? You need a load balancer. You need to deploy that. You need to configure that. You can either do it in the same host or in a different host, and so many things, right? Now, so my next and fundamental question is, can you convert the same host from which you are making the call to this upstream service into a load balancer using no external load balancing software but just common Linux utility tools, right? So let me rephrase it. Can you use usual readily available Linux utility tools to convert any given Linux host into a load balancer? So that's the question. Can you do that? So if you can do that, you do not need any external load balancing software, but you can convert your existing Linux host into a load balancer and use that to make the call to that upstream services. So is there any way you can create as many virtual IPs as you want on the current machine? And not only that, when you make a call to that VIP or that virtual IP, which perhaps maybe doesn't even exist, but it's a virtual IP, whenever you make that call to that local virtual IP, Linux will take care of proxying that request to that upstream service. And not only that, while proxying, it will also load balance. It won't always send your request to the same host, but it will load balance it across all the hosts on which the service is deployed. So can we do something like that? And interestingly, this is possible, right? You can convert any Linux host into a load balancer using the very common Linux utility called iptables. Using iptables, you can convert any Linux machine into a fully functional load balancer, all using nothing but iptable rules, right? So yep, in this video we are going to see how we can do that, how we can convert any Linux host into a load balancer using iptables. Not only that, what we will do in this video is we will set up a tiny Flask application. Like you can perhaps use any application. I'll just go with a tiny Python Flask application. I will deploy that application in 3 different instances, and then from my main instance I will be making a call. I won't be using any load balancing software but just iptables on the main instance, and from that I'll create a virtual IP, and using iptables I will proxy the connection, the request, the upstream request to all the instances which hosts our application And while doing so, I'll also make sure that the traffic is load balanced among all the instances. So yep, let's see how we can do it using iptables. And as always, without further delay, let's get started. Okay, so before getting into the implementation, let's try to visualize once what we are actually trying to achieve here, right? And not only that, let's also discuss a bit about the test environment or the lab that we'll be using to test this entire flow, right? So the thing is that it's not possible to have multiple Linux instances, like standalone Linux instances. So what I'll try to do over here is use different Docker containers to simulate the application instances, and one dedicated Docker container which will act as a Linux host which wants to make the call to that upstream service which is distributed among the different instances, right? So let's try to visualize this a bit. So for example, we have got this box or this Linux instance which is our host. So this is our main Linux host. Let's simply call it host 1. Let's keep it simple. Let's say the IP of this host is something like 172.17.0.2. I mean, those of you who are familiar with Docker, you would have recognized that this is the default Docker bridge subnet, right? Default Docker bridge subnet, which starts from 172.117.0.1, which is your host, and as in when you create containers, it increases to 3, 4, and that like that. So yeah, since Docker would be my test lab, I'm just using these IPs for the example. And let's say now we have got 3 different Linux instances and where our application is running. So let's call it app server 1, app server 2, and app server 3, right? So these are our 3 application instances or application servers. So these are the exactly same copy of the application that's running on these 3 machines or these 3 instances, right? And let's give them IPs as well, right? Let's call it 172.170.0.3, 172.17.0.4, and 172.17.0.5, right? And now what we are trying to do is that whenever an application running in this host tries to contact this service or makes a call to this service, that call should get distributed among these 3 instances. So how it gets distributed, whether it's random, it's round robin, we can decide that later, but the main criteria is it should get distributed among these 3 services. So in a way, I want to make call to this, I want my traffic to this particular service. Let's call the service app. Whenever I'm making a call to this service app, it should get distributed to app server 1, app server 2, and app s3 or app server 3. Now in this case, as you can understand that this host and these 3 app servers are connected to something called the Docker bridge, the Docker bridge network, but in reality it can be any router, right? So basically this host is also connected to this bridge or router, and it's connected to these three servers. Now it could very well be in a NAT box or a router, or what I mean to say is that instead of having 170.17.0.3, it could have been something like 172.18.0.5, or it could have been something completely different subnet altogether. It could have been 10.1.1.5, something like that. What I mean to say is that the IP doesn't matter as long as these IPs can be contacted from this particular host. We are good with it. Now the problem that we want to solve it is how we can convert this host into a load balancer implicitly, such that it can round robin or somehow distribute the traffic between these 3 servers, right? So what we want to achieve here, let's say there is a client here, there is a client C running on this host, and let's say we want to have a virtual IP in this host, let's say something called 10.10.1.100, right? Whenever this client C running in this host makes a call to this IP 10.10.1.100, which is a completely virtual IP, it's not attached to any interface, right? What I want to do is I want to distribute this traffic to these three instances, these three different instances, right? I want to round robin or randomly distribute this traffic to these three app instances. So it can be any random virtual IP. It doesn't need to belong to any subnet or anything like that. It can be 10.2.100.100, something like that, right? So whenever network calls are made to this IP, we should be able to somehow those calls should get redirected or proxied or forwarded, whatever you call it, one of these three instances, right? So that's what we are trying to solve here. Okay, so before jumping into iptables and how we can use iptables to solve this problem, I want to ask you, like, can you think of any similar situation or an analogical system where we use this kind of solution for load balancing, right? So can you think of any other system where you might be using this methodology, like you are using iptables or some similar Linux utility to convert that host into a load balancer and load balance traffic to a few local IPs or IPs in the same network or whatever. Like basically you are load balancing outgoing traffic among certain number of instances, application instances. Can you think of any such use case? So take your time, and if you can think of any such use case, do comment below. So one of the most popular use case of this methodology of converting a Linux host into a pseudo load balancer is somewhat used by Kubernetes, right? If you have used Kubernetes, you would know that a very common form of Kubernetes. So there is an entire service object in Kubernetes, right, which allows you to use your pods. So you in Kubernetes you generate pods. Let's say you have a replica set which spawns 3 pods, right? You have a replica set that spawns 3 instances of a pod, and then you want to expose the service hosted on this or the application hosted in this pod via some deployment or something to other pods or other services. The first thing you would want to do, rather than accessing the pods by their IP, which is a very bad practice, what you would want to do is you would create another abstraction or another Kubernetes object which is called a service, and using labels you can tell this service that, hey, whatever request you are getting, just route this to these pods. And one of the most basic and common type of Kubernetes service is cluster IP. What it basically does is it designates a IP for this service from a given subnet, and whenever some other pod P, let's say P, makes a request to this cluster IP service using that particular designated IP, it would somehow route this traffic to one of these 3 pods, right? So there you have it. You have a inbuilt load balancer in form of cluster IP out of the box with Kubernetes. But just remember, when you are setting up Kubernetes using kubedm or anything like that, are you installing a load balancer? Are you installing a separate load balancer for the requirement of cluster IP? No, right? I mean, if you are creating a service of type load balancer, at that time Kubernetes would use the underlying platform's facilities to spawn a load balancer. For example, in case of AWS, it might spawn a ELB, right? But if you just spawn a cluster IP, and which is local to the cluster, and if you send a request to that cluster IP, you are not, it will automatically get load balanced among all the different pods that the cluster IP is watching after. You will never have to install a separate load balancer just for the sake of cluster IP. So how does it do it? So how does that work? Turns out kubeproxy does something similar, right? Kubeproxy takes the help of either iptables or IPVS, the netfilter ecosystem, to create those rules or create those iptable or IPVS rules in each and every host where the required pods are running, or where the required client pods are running, so that those client pods can access those service pods using this cluster IP, right? So coming back to my initial question, one analogical system where this kind of trick or methodology is used for load balancing purposes is Kubernetes, right? So okay, so that's a bit of a context there, why you would want to do something like that. And even things like IPVS and those kind of things also to some extent take some similar approach to do this kind of load balancing, right? So let's say when the client first generates a packet destined for 10.10.1.100. Okay, so before that, let's say that our app instances are, or rather our applications are running on port 55555 55555 and 55555. So basically our app port is 55555. Yep, too many fives. But anyways, let's say the imaginary port on the front end server, or rather the imaginary port in our Linux host where we want to connect to in order to connect to these services is something like 44444, right? So basically whenever the client on the host wants to connect or send request to the application, it needs to make a call to 10.10.1.100 colon 44444, right? That's what we want to do, right? Coming back to our flow. So the moment the client generates a packet for this application instance, somehow if we could, or if the kernel could override this IP, right? Override this IP, overwrite it with the destination IP of the actual application server, that is 172, for example 172.0.3. If somehow it could override the imaginary virtual IP to the IP of the actual server, and if somehow it could override the port to 55555, then pretty much our problem is solved, right? Isn't it? If we can do that, it means that just before the routing decision happens in this host, and just after the packet has been generated, if at that point in time we could override this IP 10.10.1.100 with 170.18.0.3, it's important that we do it before the routing decision has been taken, because the kernel still needs to find out a way to the new destination application, right? So that's why we need to do it before the routing decision has been taken or the routing table has been consulted. So if we can do that, pretty much our problem is solved. Now the packet post routing, it will go to one of the servers. How it load balances is a different thing, but for the proxy part, or for the forwarding part, that takes care of it, isn't it? And since the packet that's originating from the host, that is host 1, by default its source IP will always be the IP of this box, which is 170.17.0.2. We do not have to think about how the packet will come back, because since that's the actual IP of the box from which the packet is originating, right? So we do not have to do anything with the source IP of the packet, since that's already of the box's packet. Had this packet been generated, had this client been located on some other external box, let's say this is C, and this box is totally acting as a pseudo load balancer or a Linux load balancer, then we would also have to bother ourselves with the source IP, because the source IP of this box would not match with the IP of this box from which the packet was being generated, right? In that case, we would have to override the source IP as well to this original client boxes or client server's IP. But in this case, since the packet is being originated from the load balancer box itself, or from the same Linux host which needs to do this load balancing or the proxying, we do not care about the source IP, but we only care about overriding the destination IP and port. Awesome. So if somehow we could figure that out, or somehow we could achieve this IP overriding or destination IP overriding using iptables, we are pretty much done, right? I mean the proxying part is pretty much done. We still need to figure out the round robin or load distribution part, but at least we are done with if we can do this, we are at least done with the proxying part. Now how can iptables help us? So you see, iptables is an extremely interesting utility and extremely powerful utility that Linux provides you. It literally allows you to mangle IPs, mangle packets and whatnot, right? You can do all those kind of things. So the iptable has some core concepts. The first thing is, so under iptables, and again this won't be a detailed video on iptables because that would need a couple of videos in itself. iptables is so vast, so descriptive, so many things can be, so comprehensive, so many things can be done with it. So I would only focus on the things that we would need in this video, right? So two of the core things, actually three of the core things that iptable provides you with is chains. So iptables is based on a kernel module called the net filter, right? And the net filter has a concept called hooks, and those hooks pretty much have a one-to-one correspondence with chains in iptables. So hooks are nothing but points in the kernel where you can actually register your own function. So when that particular hook gets triggered, your callback function gets triggered, as simple as that. So the iptables has got a few chains, and those chains correspond to those hooks in your net filter. So the chains that we will be interested in is actually the only chain in this case we will be interested in is output, the output chain. So the packet gets thrown into this chain when it's being generated inside a box, right? So this is completely different for a packet which comes to your box or comes to your host. In that case, the chain that it's first thrown into is something called pre-routing, where the kernel takes the decision that whether the packet is destined for this host or not, right? And then there is input chain, there is post routing chain, and those kind of things. So post routing chain comes into picture, or it's a hook that comes into picture once the routing decision has been taken. So that gets triggered in the point in time which is between the packet leaving the box and the routing decision being made, right? I just mentioned pre-routing just to show how the game changes, or how the scenario changes for a packet with respect to a packet being generated within the host and with respect to a packet incoming to the host. So that's where output and pre-routing chain comes into picture. But since in our case the packet is being generated within the box, we do not have to care about pre-routing, but we only have to care about the output chain, which means just when the packet has been generated. And there are certain, so these iptable rules for iptables, how you instruct iptables to do something with the packet is by writing rules. So that brings us to rules. So these are like small one-liner statements in itself which instructs the kernel to do something with the packet. So those rules are basically what gets converted to your functions, which gets called when a certain hook has been triggered in your net filter. That calls basically the function that you are registering, right? Or the rule that you are registering. So these rules are very nicely organized in iptables in form of tables, right? So similar rules are grouped into a table. For example, any rule that has got to do something with network address translation or NAT, that gets grouped into the NAT table. Anything that has got something to do with filtration of packets, right? Filtering packets, that gets grouped into something called filter. Again, that's filter is just another example. There are many such tables, but again, we will concern ourselves only with the NAT table for now. Why do we concern ourselves only with the NAT table in this case? Because that's what we are going to do, right? This entire scheme of overriding the destination IP with a different destination IP is basically network address translation, not the usual one that we do on routers for accessing the internet, but a different one which is called destination NAT, where we are changing the destination IP, the destination for which the IP is bound. We are changing that destination IP to a new destination IP, right? So that's why it's called destination NAT or DNAT. And finally, there are certain things called action. So what do you want to do with the packet? And again, there are multiple such actions, and there can be accept, which means you accept the packet for the host. There is drop, which means just stop processing the packet. And there are things like DNAT, SNAT. Again, since I mentioned that the packet is generated within the box, you do not have to concern yourself with overriding or changing the source IP of the packet. So destination NAT is not in the scope of this video, right? We do not bother ourselves with SNAT, but we do bother ourselves with DNAT, right? This is what we'll be using. So in the NAT table for the output chain, if we can use destination NAT to override the destination IP of the packet being generated to one of the IPs of the boxes on which the actual application is hosted, our problem is solved, right? We can basically proxy the packet to one of the destination servers, and that's pretty much what we are going to do now. We are going to create this iptable rules which will make sure that for any packet that gets generated within the box for this virtual IP 10.10.1.100, which is completely imaginary, it doesn't even exist, right? Anything that gets generated from within the box for this IP 10.10.1.100, we are going to DNAT that packet and make it go to one of these box IPs, or basically Docker instance, Docker container IPs, right? And the next part that's remaining to be solved is how do we make it go to one of these boxes, because whatever discussion we just had till now, from there we can it seems like every time it will go to one particular box, but how do we make it choose one of the three boxes? Well, there is a module in iptables for that which comes to our rescue in this case, which is called -m. I mean, it's a switch for modules, and also it's an iptable module which is called statistic. So the module statistic provides us with different modes and algorithms to send packet to one of the servers of this of multiple servers or these three servers, right? It provides us with multiple algorithms which in order to select which server we want to proxy our request to, right? Which is extremely interesting once again. So instead of going over how -m works in theory, let's see it in practice. Let's see how we can create these iptable rules and how we can use the statistic module in iptables to actually create a load balancer, to actually convert the Linux host into a load balancer for any packet being generated within the box and to send it to one of the three actual application instances via this virtual IP. So let's see how we can do that. Okay, so first let's create our dummy applications, right? Not dummy applications, but very simple application Python applications which will act as our destination servers or destination Docker containers. Again, so in this case, in our lab, we will be having one Docker container which will act as a load balancer, which will have our imaginary client, which is curl in this case, right? We'll keep it simple, and then we will have three other containers which will actually run the application. And since it's Docker, everything will be connected to the local Docker bridge, like the Docker 0 bridge. So they will have IPs in the range, IPs of the type 172.17.0.xyz. And again, like in this case, it's been connected using Docker bridge, but it could have been anything, right? It could have been connected via router to a different IP subnet altogether. So what I mean is that our box which generates the traffic, it might be connected to two interfaces, right? With like one with a user facing interface and one with another internal interface, right? Where the application servers are. So it can be anything like that. As long as we have access to the actual IPs of the servers, we are good to go, right? So I'll quickly create a very, very tiny Flask application, and it will reside in this app.py, and let's get done with it. From Flask, import Flask. We don't need request actually. App will create the main Flask app. So the app will be listening on all the interfaces in the container, and it will be listening on port 55555 as discussed, right? So it's a very simple app. All it does is that before first request, just when the first request is made, it gets the host name of the host, and it stores it in a variable called hostname in app.config. So config is something which will remain for the entire lifetime of app object, which means it will remain for the entire lifetime of the service or the application. We have a single route called /ping. This is what we'll be pinging, and it simply says hello from host. This will allow us to differentiate between the responses generated from the different hosts, which will let us know actually if it's being round robin or not. Finally, we just make it listen on all the interfaces and port 55555, right? That's that. Now I'll quickly make a tiny Docker file for this. I'll call it I'll call it app.docker file, and let me quickly write this. So my base image will be Python. And that's it. That's our very tiny Docker file. It extends from the Python image. I just copy the app.py, I install the dependencies, and I simply run it using Python 3 app.py. That's it, right? Okay, right? And let's quickly build this image and make sure everything is running as expected. So I'll do a Docker. Actually, -t The image name I'll use is lb app v1, and since I'm not using the standard Docker file name, I will have to use the -f flag, and I've called it app.docker file and dot for the build context. Okay, so my bad. Okay, I made a mistake. It should be v1. Spelled it again. Okay, so our image is built. Let's see. Here is our image, lb-app. So let's try to run it. Sudo docker run fnrm, and the name of the image is lb app v1, and that's it. And the app has started. It's running on 170.17.0.2, which is expected. Let's split the terminal quickly. Let's do a curl call. Remember, we did not expose the port, neither did we do a port mapping, so we cannot use 127.0.0.1, but we need to use 172.17.0.2. My bad. We should do ping, and it works. So hello from host e4 f5, whatever it is, that's the host name, right? Okay, so that's that. And now our app is at least up and running. So now I'll just write a very tiny script to spawn 3 versions of this, basically 3 instances of this application, and again it will be a very quick thing. Set up apps.sh. So I want to give the containers separate names, so I'll do app1, app2, app3, right? And now I'll simply loop over them. Just a nice info that it's going to start the app, and I'm going to do this docker run fnrm -it -t. So I want to put it in the background so that I can start all the three containers. I want to give the container a name, as I mentioned, lb, what was the name again? It was lb-app v1, right? And that's it. Done. App1, app2, app3, right? Actually, I don't need this -it. I don't know why did I do that. Yeah, just -rm -d is fine. And let me just do a chmod +x set up apps.sh. Yep, it's now executable. Okay, so let's try to run these 3 containers now. Okay, that ran our 3 containers, and so remember, this time the IPs should be 0.2, 0.3, and 0.4. So let's try curling all of them. That works. That came from the first one, I believe. FD2F0788, right? And then comes 3, and then comes 4. Okay, all done. Cool. So that's that. Our containers are up. Again, the reason I'm writing this script, so I'll push it to GitHub so that you all can also run this experiment on your local. It's more like a lab setup. And now I'm going to create a new Docker file which will going to act as the client machine or the client host, which we will also try to convert into a LB for these 3 upstream apps. So let's do that, and I'll call it host.docker Dockerfile. I could have called it lb.dockerfile, but then again, that host is not just an lb, right? It's a host where multiple services can be running, applications can be running, and among all such services, there shall be one service which acts as a client for this upstream application, right? So it's not just an lb, but it's a normal Linux host which wants to make a connection to this upstream application, and we want to convert it into, or rather we want to impart some load balancing capabilities to that host, right? So let's do that, and it will be a very tiny Docker file. We will extend it from Ubuntu actually, since it's a multi-purpose host. It can have Python, it cannot have Python, who knows. So I'll do a apt update as usual. Actually, we do not need ncat anymore. Ncat is good for just testing quickly, but anyways, I'll just leave it there. IP out to, it's good to have. You can see the different IP addresses and things like that present on the container, and vim just in case we need to edit something. We mostly will not, but I just like putting in vim there in case I need it for anything and everything, right? I mean, it's just a lab, right? It doesn't have to be production optimized. Okay, and its entry point will be bin bash. Okay, that's our Docker file. Now let's build it. Sudo docker build -t lb host to make a distinguish from lb app, and we call it v1. We give it a tag of v1, or rather version v1. Again, I need to mention the Docker file, which is host.dockerfile, and the context, and let's build it. Okay, that's done, and now let's try to run it. Run this Docker file, or run this host container. Sudo docker run -rm -it, because we want to interact with it, and the name is lb host, and yeah, I mean, we have done cmd bin bash, so it should be fine. Of course it couldn't find. Now it should be able to find, and it gave us a shell. So first let's see what IP did it get. It got 172.17.0.5, which makes sense because 234 is for the app, has already been assigned to the app containers, so this one got 0.5. and let's see if I can access. So oh great, I forgot to add curl. Let me just quickly add it here so that I don't forget before I push it to GitHub. Yeah, this is the one, and curl. Okay, let's quickly install curl. Okay, curl should now be installed, and what we are going to do is, let's see if at least this one is accessible. Yes, it is, which is all good because it's supposed to have access to all the app containers because it's on the same bridge network. So now, what if, so our designated IP VIP, that our imaginary virtual IP was 10.10.10.10.1.100. Let's see if we can, and the port was 44444. Let's see if we can access anything there. 10.10.1.100 44444, and the answer is obvious, which should be, of course it cannot access anything, and that's why curl is hanging, right? So if you do a verbose, it will just tell you that it's trying to access 44444 on 10.10.1.100, which means clearly the virtual IP has got no value yet, right? Of course, and that's expected. Let's now try to add our iptable rule, which will proxy it to the one of the upstream, not yet load balance right now, but just proxy it to one of the hosts. Before that, we need to if you are trying it out on your local machine, or not container, but let's say a virtual machine or your local machine, you need to make sure one thing, that IPv4 forwarding is switched on. Otherwise it might not be able to forward packets. Let's see for this container if it's switched on or not. So to check that, you can either use sysctl, or you can simply do a cat on /proc sys net IPv4, and it's called forwarding, something called forwarding IP forward, yeah, and it has got a value of 1, which means it's enabled, right? Okay, so now coming to our actual interesting thing, the iptable rule, right? So let's go step by step. First, let's see if iptable is present. It's present. Let's see if our nat table has got anything. Okay, so it didn't allow me to run the iptables command. It says that it doesn't have the permission, like the user doesn't have permission, you must be root. But if, as you can see, I'm already root. So you might keep thinking, why, although I am root, but it thinks I am not root? The reason is the capability that the container needs is the netadmin capability. Without that, you cannot access iptables command from within the Docker container, even if you have the iptables command installed, and even if you are root, right? So let's quickly do that. So the command is -cap add equal to net admin. Yep. Once again, I'm in shell, and sadly, once again, I need to install curl. Now, once again, let's see if it's there. It is there. Let's see our if there are any present rules in the nat table. There is none. Now let's add the iptable rule for overriding the destination IP whenever a packet is generated for 10.10.10.1.100 and port 44444. So what I'll do is iptables -t nat, because I am making the change to the nat table. As simple as that. Inside the nat table, I want to append to the output chain, right? As discussed, since the packet is being generated within the host, I need to use the output chain. So output. Now I need to tell this rule to get executed whenever it matches the IP of the VIP, or rather whenever it matches the VIP, right? So for that, I'll do -d, and which is destination. So I'm saying that if destination IP matches 10.10.1.100, protocol is TCP. What's the destination port that I want to match? That's 44444. And what I want to do with the packet, I want to DNAT it to what? To destination 172.17.0. Let's go with 2, right? Let's go with 2 for now. And to which port I want to override? I want to override it to 5, which is our port where the application is running on that container. So what it says in short is, in the nat table, append to the output chain that if any packet matches the destination IP 10.10.1.100 and protocol TCP and destination port 44444, that is 5 fours, do a DNAT to destination 172.17.0.2 and port should be 55555. Let's do this. Okay, so now if I do a iptables -t nat -l, we can see the rule active, right, in under the output chain in table nat. So now let's try to do the same thing once again. We'll do curl 10.10.1.100 44444/ping, and let's see if we get response from the upstream application. And we got. That's awesome, right? We made the request to a completely imaginary IP, which is 10.10.1.100 on an imaginary port which is not even active, 44444, and it got routed, or rather proxied, to our actual host, which is FD2F0788. Remember, this was the ID of the first container, that is app1 container. So if I do quickly, if I do a docker ts, so isn't it app1 FD2F078848F6, right? So we got the reply from app1's server, right? Basically app1 container which is running our service. So the forwarding works completely fine, right? And we can actually do one more thing. We can actually go to our docker exec -it fd2 bin bash, right? We can do this, and let me quickly install tcp dump. And let's, okay, IP is not present, but never mind. The default interface would be @0 @ if something something. So what I can simply do here is -tcp dump -i @0. Let's monitor what's happening on @0. And now if I do this, look at this. So the packet was proxied to this container and it got the packet. So it came from 170.17.0.5, which is the IP of this container, to this host, which is this one, 8848F6, and from there, and this was a source port. Yeah, source port can be whatever, pretty much. And once it was done, it was able to reply back to this host, which is 0.5, whatever the port it is. Like 0.5 is are this host from which is generating the request. And so basically, I mean, it's for the different TCP packets. But yeah, overall, this shows that the packet was actually routed and it landed on the upstream server, right? Now comes the other interesting part, which is how can we make it round robin, right? So again, as I mentioned, I'll be using the statistic module. I'll be showing the round robin thing here. You can also do a random thing using, so basically the statistic modules has a switch called mode, and this mode determines which algorithm will be used. So if you select a mode nth means pretty much which you are saying which server to hit on which turn. So basically using that you can do something like a round robin. There is a mode called random, which takes an additional parameter called probability, right? And there you can give a probability with which a certain iptable rule is selected. So just imagine, like, we used this iptable rule, right, to do the override. So one thing that would often come to our mind is what if we simply replicate this rule thrice, right? Once for 0.2, which is this one, another for host 0.3, another for 0.4, 0.4, 2, 3, 4. Sadly, iptables doesn't work like that. It's synchronous. The first rule that gets smashed gets executed, right? So all the traffic would keep on going to 170.17.0.2, right? And there's the whole reason we cannot do that. We need to use the statistic module. So the random module, it assigns a probability to each rule with which it will get executed, and the nth module simply tells at a given turn for that rule's execution which destination server will be selected. It might be a bit tricky to explain, so let's see it by example, right? So for that, what I'll do is I will quickly flush the iptables. I just want them to be in nice order. So this is for flush. Whenever you are using this, be very mindful of the fact that it will completely wipe out your selected iptable. So in this case, NAT will be completely wiped out. Let's check. Yep, it's wiped out. Okay, so what I'm going to do is I'm going to use the nth mode or nth algorithm, do a round robin. So let's do that. iptables -nat -a output -d 10.1.100 sorry 10.10.1.100 -tcp -d port 44444 -m statistic, the module hyphen mode. Now comes the mode nth, which is also the algorithm, hyphen every. So for the first rule, which will point to, let's say, 170.17.0.2 server, I want this rule to be executed every, let's say, third packet. So every third packet, this rule will get executed, right? Otherwise it will be ignored. And this rule would be for 172.17.0.2, which in other words it means is that every third packet, starting from 0th packet, every third packet, or rather if I consider base indexing to be 0, 0, 1, 2, the second packet would go to 172.17.0.2 because of this rule which will get executed. So I'll just have to say -every 3, at which packet the entire loop starts. It starts at 0, Again the same thing, hyphen j dnat hyphen 2 destination 170.17.0 dot what was it 2 and 55555, right? As simple as that. So it's the same thing, hyphen tnet hyphen output hyphen d10.10.100 hyphen ptcp hyphen fn d. Okay, that's a mistake, it should be dport 44444 hyphen m statistic hyphen fn mode nth hyphen fn every third packet, or every third packet hyphen fn packet 0, it starts from the 0th packet hyphen j dnet to destination, the upstream container. Cool. Again for the next thing, that is 3, what I'll do is I'll make it 2, right? This should happen for the second packet, or 0 1 2 as in the first packet if you consider base indexing. And for the last one we do not have to mention anything, right? If nothing matches, this should match. So I'll simply remove this. No m statistic, nothing. And also this should be 4. Done, right? So now let's see. Once again, let me just exit this container and let me do a docker ps. So these are our host names. So let's do a curl now. So let's make a few calls to the service, right? So let's do a curl 10.10.1.100 44444 ping. Okay, so now the call was routed to the first app instance, which is fd2f. That matches. What happens if I do another call, curl call? This time it went to 1 db, which is app2 1 db, and if I do it again, it goes to 6a1, which is the third app instance. So it's a perfect round robin, app1 app2 app3. What happens if I do again? It comes back to fd2f, which is app1, and it repeats. So it's a perfect round robin that's happening among the 3 upstream servers, right? So yeah, just like that, we have a out of the box load balancer without installing any extra softwares on our Linux host, right? Using nothing but iptables. I mean, yeah, it's not a full-fledged load balancer. A load balancer does health check. It monitors when a upstream becomes unhealthy so that it doesn't send any route any traffic to that well. All of those you can do as well, right? All you need to do is create some daemons which monitors the unhealthy upstream server, and it removes it and changes the iptable rules, right? Those things can also be done. But what I'm trying to say is that using just a few iptable rules, you could add load balancing capabilities to a normal Linux box, right? So that's the power of iptables. So the other thing we could have done is use the random mode or the random algorithm, which also takes a probability with which it would send a with which it would match a rule so that the traffic gets sent to that a particular server. So how can we do that? Well, once again what I'll do is I'll simply flush all the iptable rules, nat table rules, right? And now let's once again start adding them, but this time we won't be using the nth mode but the random mode. So this is the first server, and I'll simply remove everything. Okay, statistic we need -m statistic, yeah. And what we'll do is mode random -- probability 0.33. So what this basically means is that 33% of the time this rule will match. Okay, rest of the time the other rules will match, which we will add soon. So let's add this. So now the second one, which is 3, and this time I'll make sure this matches 66% of the time, but actually this is not 66% of the time. Why? Because 33% of the time the first rule is matching, right? So if you remove 33 from 66, so the second rule is also matching 33% of the time, right? Okay, and this will be 3, and when nothing matches, we have the third server, which gets executed when nothing matches. So let's do that as well. Okay, now once again let's do our curl. So this time it's the app1. Now it went to app3, not app2 but app3, because it's random. Now this time it's app2, and again it's app1, app2, again app2, and we got app 3, and again F1. So yeah, it's completely random. So again, we have a randomized load balancing capability added to the Linux host, right? How cool is that? You out of the box, you have just two load balancing algorithms. I haven't explored more on the statistic module, but yeah, I'm pretty sure there are more capabilities that can be implemented with that module and iptables as a whole, right? And also one more thing we should note here is that it's not that you can just create one VIP or one virtual IP, right? You can create another virtual IP and you can point those to a separate bunch of servers, right? You just have to, let's say you want a new virtual IP, let's say 10.10.1.200, and you want to make it point to some other upstream servers. No problem at all. You just need to add another bunch of iptable rules so that new VIP, the new virtual IP points to the new set of upstream servers, right? And it's that simple. So if you just convert this entire thing into a script which takes the server IP as input and the virtual IP as an input and the ports as an input, you can simply automate the creation of these iptable rules. It's as simple as that, right? So yeah, that's pretty much what I wanted to discuss in this video. I wanted to show this cool feature provided by iptables and how you can convert literally any Linux host into a kind of a load balancer, or you can add load balancing capability to any Linux host without adding any external load balancing software, and how you can do this kind of proxying to how you can change the destination IP to a different destination IP and do this kind of proxying and load balancing, right? So yeah, so let me know in the comment section if you have used this technique in any of your projects or in your work, or if you know of any other use case that this can potentially have, or if you know of any other technology or tool which already uses this method to create routing / create proxying, to create a proxy or load balancing capabilities, right? So yeah, thanks for watching this video and see you all next time.